As we have mentioned earlier, configuration is a kind of design, a kind of routine design. And one method for doing configuration is plan refinement. In configuration, all the components of the design are already known, but we have to find some arrangement for the components, and we assign values to some of the variables of those components to arrive at an arrangement. Here is a design specification that one begins with. Here it might be a plan for designing a chair as a whole. And once we assign values to some of the variables at the level of the chair, then we can refine the plan for the chair into a plan for the chair legs, the chair seat, and so on. All of this might be subject to certain constraints. There are in fact a number of AI systems that do configuration design. Many of them are being used in industry. Some of these AI systems use methods like plan refinement, the way we have shown it here. Others use case-based reasoning. In fact, AI systems use a variety of methods for doing configuration design, including model-based reasoning and rule-based reasoning. What about more creative kinds of design? Design in which not all the parts are known in advance. Since we just discussed the flashlight example in the context of systems thinking, let us revisit that example in the context of creative design. So this is a schematic of the flashlight circuit. Here is a switch, the battery, the bulb, as earlier. Under systems thinking, we discussed how structure behavior function models capture the knowledge that when the switch is closed, electricity flows from the battery to the bulb, and the bulb converts that electrical energy into light energy. Let us suppose that this particular electrical circuit used a 1.5 volt battery and created 10 lumens of light. Tomorrow someone comes to you and says, I want 20 lumens of light, design a flashlight electrical circuit for me. How will you do that? You might go through the structure behavior function model of this particular circuit and do systems thinking. You may recognize that the amount of light created in the bulb is directly proportional to the voltage of the battery. So instead of creating 10 lumens of light, you need 20 lumens of light. You might say, I'm going to use a 3 volt battery. So far, so good. You have done systems thinking in the context of design thinking. But now let us add a wrinkle. Suppose that a 3.0 volt battery is not available. At this point, a teacher tells you it's okay if a 3.0 volt battery is not available. You can connect two 1.0 volt batteries in series. Two 1.5 volt batteries connected in series will give you the voltage of 3 volts. Accepting the teacher's advice, you can now create an electrical circuit that will use two 1.4 volt batteries in series and create light of 20 lumens. But you not just created this particular design, you also learned something from it. Every time you create a design, every experience is an opportunity for learning. In the mid-1990s, Sam Bhatta here at Georgia Tech created a program called IDEAL. IDEAL did creative design. In particular, IDEAL would learn about design patterns from simple design cases, the kind we just talked about. I'm sure most of you are familiar with the notion of design pattern. Design patterns are a major construct in software engineering. But design patterns occur not just in software engineering, but in all kinds of design, for example, architecture and engineering and so on. Here is Sam's way of capturing the design pattern that can be learned from the previous case. If you know the design of a device that changes the value of some variable from one value to another value, and you want another design that changes the value of the same variable to some other value, not the same as the previous design, one way in which you can create the new design is by replicating the behavior of the previous design. So not just having behavior B1 for the first design, but having this behavior B1 as many times as needed. Let us connect this to the example we just saw. If you have a design of an electrical circuit that can create 10 lumens of light, and you know how to do it through some behavior B1, I need to design an electrical circuit that can create 20 lumens of light, but you don't know the behavior B2. Then, this behavior B2 is a replication of the behavior B1 by connecting components in series. Once Sam's program IDEAL had learned about this design pattern of cascading, of replication, then when it was given the problem of designing a water pump of higher capacity than the one available, it could create a new water pump by connecting several water pumps in series. Thus, IDEAL created new designs in one domain, the domain of water pump, through analogical transfer of design patterns learned in another domain, the domain of electrical circuits. Viewed from the perspective of the new domain of water pumps, initially did not know about all the components, about all the water pumps that will be needed. But Sam's program ideal was creative enough to know that the pattern of problems here in water pump is exactly the same pattern that was also occurring in the domain of electrical circuits. Sam's theory provides a computational account of not only how design patterns can be used, but also about how these design patterns can be learned and transferred to new domains. There is, of course, a lot more to design. We said earlier that design thinking engages problem-solution coevolution. It's not just that the solution evolves while the problem remains fixed, but that the problem evolves even as the solution evolves. It's not yet clear how humans do this kind of creative design where there is problem-solution coevolution. There certainly are few AI systems capable of problem-solution coevolution at present.